in which for lambda class. In this video, we're going to discuss roots of polynomials and field extensions. Field extensions are going to be a very useful thing for us. We're going to build new fields out of given ones in a very particular way. So let's fix a base field K. Let's call it K. So what is a field? A field is a commutative ring in which every element has an inverse. Remember, a field is a commutative ring in which every non-zero element is invertible. Okay? So what does it mean to be a commutative ring? Okay, it's a ring in which the multiplication is a commutative operation. Okay, and what does it mean to say that every non-zero element is invertible? Well, you take a non-zero element in that ring and it has a multiplicative inverse. Okay, so examples for us, the rational numbers. Rational numbers form a commutative ring because multiplication of rationals is commutative, and every non-zero fraction has an inverse. Say you take the fraction a over b, its inverse is simply b over a. If you multiply these two guys together, then what you get is a times b over b times a, and these two guys simplify out and you get 1. So this is one of the first fields that we learn how to use. That happens usually in middle school. Then we have more examples for this. Say another example, the real numbers. Multiplication of reals is commutative, and every real number that is non-zero has an inverse. Say the inverse of the square root of 2 is simply 1 over the square root of 2, which can be written as square root of 2 over 2, right? If you multiply together square root of 2 times square root of 2 over 2, what you get is square root of 2 times square root of 2 over 2. And this is by definition 2 over 2, which is 1 after simplification. And then we have more examples, right? We have the examples that come from finite fields. Sets of 3, the class of 0, the class of 1, and the class of 2. Okay, the remainders of dividing by 3. Here multiplication is obviously commutative, and we also have inverses. Say the inverse of 2 is actually the class of 2, since if you multiply these guys together, what you get is 2 times 2, and you take class, and this is the class of 4. And to see what the class of 4 is, you divide 4 by 3 and look at the remainder, which is 1. So the inverse for the class of 2 is the class of 2. Okay, so we have fields, we have worked with them through high school, and we have learned how to build finite fields. So that's what a field is, right? And we're going to talk about polynomials over a field. So let K be a field we will call K the base field. Then we are going to look at K of X, which is the set of all polynomials with coefficients in K. So this is simply a set, right? But K is endowed with addition and multiplication. K of X becomes a commutative ring with the usual addition and multiplication of polynomials. So you multiply out and use the fact that powers of X add up together. Say, for example, for instance, first example, let's take a look at polynomials in R of X. Take polynomial f of x, square root of 2 plus 3x, and then take g of x as 3 plus square root of 2 times x minus x squared. You know how to, for instance, take addition. The addition of f and g at x is simply adding power-wise. So this will be square root of 2 plus 3 plus 3 plus the square root of 2 times x minus x squared. So we end up adding power-wise. So we know how to add polynomials. This is frankly an operation that we have done before. And the same goes with multiplication. What's the multiplication of f and g at x? Well, you have to multiply together polynomials, remembering how to operate with the x's. And this is merely distribution and addition together. So this is 3 times the square root of 2 plus 2 times x minus square root of 2 times x squared plus 9x plus 3 square root of 2 x squared minus 3x cubed. So that's the polynomial f times g at x. If we want, we can reorganize this and write it in ascending powers. So we get 3 times square root of 2 plus 11 times x. And then we get plus 2 square root of 2 x squared minus 3x cubed. So we know how to do this, okay? We have that k of x with the usual addition and multiplication becomes a commutative ring. Becomes a commutative ring. Okay, and this ring is very special. We have a theorem which we're going to state that k field implies that k of x has a division algorithm, usually called the Euclidean division algorithm. And it goes like this. Let f and g be two polynomials in k of x such that the degree of f is greater or equal to the degree of g, right? So then there exist unique p of x and r of x, let's call it q of x, in the same set of polynomials such that f of x can be written as q of x times g of x plus r of x. And the very important thing is that this r of x, this polynomial r, needs to satisfy a very strong condition. 0 has to be less or equal to the degree of r and needs to be strictly less than the degree of g. Okay, so g is a divisor, q is the quotient, and r is the remainder. Okay, so this pretty much emulates what we have learned in high school. Okay, so the only difference is now that we need to measure polynomials with their degree. The degree function allows us to measure how big polynomials are in a very specific sense. Okay, so this is actually a theorem and it can be proved. We will not do this in this video, but we will prove this in a separate video. Okay, we will prove that whenever we have a field, k of x has a division algorithm. But for us, for now, we need to understand that whenever we have two polynomials, we can obtain q and r such that this writing is possible. Okay, maybe we can try to give an example. Let's try q equal to k equal to q, and let's choose f of x being 2 plus 3x plus 2x squared, and let's try to divide it with g of x being 1 plus x. So how do we divide these two together? Well, we just write f and g in descending order and make what we call long division. This is something that maybe you remember from school, right? So this scheme allows us to make multiplications very easily. We need to see how do we get to 2 times x squared using x, and that's 2x times x gives us 2x squared. Now 2x times 1, that gives us 2x. And since we're done multiplying, now we take this fraction. This first part vanishes, and then we get just x. 3x's minus 2x's gives us just x. Now we drop down number 2, and we go again, because this one has a degree which is not smaller than this degree, just 1. And now it's easy. So to get to x, we just multiply by 1. 1 times x is x. 1 times 1 gives us 1. We subtract, and we get just 1. Since this guy has degree 0, the algorithm finishes. what you get here is that you can write f as the quotient times the divisor plus the remainder. This one's f, this one is q, this one is g, and this guy over here is just r. Okay, so this is a very basic example of how this algorithm works. Okay, so we have that. Let's go with some definitions. Definitions. We say that G divides F if and only if R is 0 in the that is, if there exists a polynomial Q in the same set of polynomials such that F equals Q times G. In this case, the remainder is the constant 0. Okay, that's the definition. Another definition. This is simply a special case. The polynomial x minus a divides f if and only if f of a equals 0. It's not a definition, this is a theorem. Come on. This is theorem. Polynomial x minus a divides f if and only if f of a equals 0. That is, x minus a divides f if and only if a is a root of f. And this is a very important theorem because it relates roots of a polynomial to factors of a polynomial. Okay, and this is very easy to prove. Let g of x be x minus a, and this says that the degree of g is equal to 1. Then, by the Euclidean algorithm, f of x can be written as q of x times x minus a plus r of x, where the remainder needs to have a degree which is greater or equal to 0 and strictly less than 1. But if the degree is strictly less than 1, this means that r is a constant. Okay, so if r is a constant, then we're all set, because this says that f of x can be written as q of x times x minus a plus a constant. So this is all pretty much for free, right? The low degree of g and the Euclidean algorithm force r to be a constant. It's a constant polynomial. And now we get to prove what we want. If a is a root for f, then what we get is 0 equals f of a, which is in turn q at a times a minus a plus r, which is replaced x with a, and this vanishes to 0, and this gives that the r is 0. So r, which is a constant, is the 0 constant. So with this we have proved that if a is root for f, then the remainder is 0, right? And we also have conversely, if r is 0, then we can write this, and then f of a will equal 0. Okay, so that's really easy. That's really easy. So there's a relation, observation. This theorem gives a link between roots of a polynomial f and factors of f, specifically linear factors. Say x naught is a root, which means that f at x naught equals 0 if and only if f can be factored. It can be written as q of x times x minus x naught. This is what we call a factor of x, and it's a linear factor. We call it linear factor because it's a polynomial of degree 1. Okay, so whenever this can be done, allows us to reduce the problem of studying f to the problem of studying q, which is a polynomial which has a 1 degree less than f. So going down in the degree is actually something very desirable because it reduces the complexity of the problem, right? We're going to write another definition, and we'll say that f in k of x is reducible if there exist two polynomials, say h of x and g of x, also q of x. So f, h, and g all belong to k of x, such that f can be factored as g times h with degree of h and degree of g strictly less than the degree of f. So a polynomial is reducible if it has factors which have degree which is strictly less than the degree of f. If a polynomial f is not reducible, then it's called irreducible. It cannot be written as a product of two polynomials of smaller degree. This is pretty much like an analog for prime numbers. Okay, a prime number is one that it cannot be factored as a product of two smaller numbers. Okay, so this definition is very important for us. We will use it very often, and it needs to be noted that we have stressed that all the polynomials involved in the factorization belong to the same set of polynomials. If f lives in k of x, then h and g also must live in k of x. And we will add something to this definition. We'll say that f in k of x is reducible in k of x if there exists h and g in k of x such that. But it needs to be noted that reducibility is always referred to the proper ring of polynomials, right? And we will say why. Examples. Let's take the first example. F of x being x squared minus 2. If we look at the polynomial f at q of x, if we consider f as a polynomial with rational coefficients, then f is irreducible. I will say why. Suppose f of x can be factored into product of two polynomials of degree 1. That's the only choice we have. Then f of x will be 0. Because if we replace x with x naught, we get 0. So what we get here is that x0 is a root of f and x naught lives in q. So if it were the case that f could be factored into two linear factors, then this x naught will be a root of f. And since this polynomial belongs to q of x, then x naught will be in q. But this is impossible. Since the bare equation f of x naught equals 0 actually is x naught squared minus 2 equals 0. So which means that x naught squared equals 2. And there is no rational number which has 2 as its square. That is, square root of 2 isn't a rational number, which is a very standard fact. So this polynomial that we have written here, if we look at the polynomial as a polynomial with coefficients in q, this polynomial is irreducible and has no roots. So if we take a look at this polynomial belonging to q of x, then we get that f is irreducible and f has no roots in q. But what happens with the fact that the rational numbers can be seen as a subset of the real numbers? What happens with that fact? This implies that polynomials in Q of x can be seen as polynomials in R of x. That is, f can be seen as belonging to polynomials with real coefficients now. And now, square root of 2, which is a real number, is a root of f. And so, f can be factored. As a matter of fact, it can be seen that we can write this factorization for f. And now these two polynomials belong to R of x. So when we look at f as belonging to this set of polynomials, the polynomials with real coefficients, it becomes reducible. We have enlarged the base field in a way that we now have factors and we now have roots. R is a field containing Q in a way that first has roots for f, and second allows us to factor f. What was once irreducible, if we enlarge the base field, it becomes reducible, it becomes factorable. Okay, so this is a very potent example. Another very known example is going one step further. What about taking k equal to r and taking a look at g of x being x squared plus 1? G has no real roots. G has no real roots. Okay, because for every b in R, then g of b is actually b squared plus 1, and this is always greater or equal to 1, which is always greater than 0. So no b in R is a root for g. But again, if R can be seen as a subset of the complex numbers, then polynomials with coefficients in R can be seen as polynomials with coefficients in C. And now, if we take a look at G as being a polynomial with coefficients in C, then G can be factored. It's the same process again and again. So in the first case, well, in the second case, C is a field which is larger than R that has a root for G. And what happened in the first example, it's pretty much the same. The real numbers are a field that contain Q and they allow a root for Q. So we're taking a look at field extensions here. We say that R is a field extension of Q, in the same way that we say that C is a field extension of R. So there's a field that contains a smaller field. In that way, we're talking about extensions. And we are now going to show a very important result, very important theorem. And we're going to prove it. Theorem, let f belong to k of x be an irreducible polynomial of degree n greater than 1, then there exists a field that contains k and also contains a root for f. So whenever we have an irreducible polynomial in k of x, we can construct a new field that contains k and also contains a root for f. And this is a very interesting result. It's a very important one and builds up on things that we have already discussed. Let's go for the proof. Okay, so k of x is a ring. Okay, and we are going to define a an equivalence relation in k of x. Let's define the equivalence relation in k of x. F will be related to g if no let's choose another. We fixed f in our theorem, so we need to use a dummy polynomial. H will be related to g in k of x if and only if f divides the difference. This means f divides h minus g, or we can also say h minus g is divisible by f. That means the Euclidean algorithm gives us a remainder of 0. Okay? So this gives us an equivalence relation. And when we have an equivalence relation, we have the projection to the quotient. The quotient set is actually the set of equivalence classes. Okay, and we have seen in a different video that whenever we have a projection to the set of the equivalence classes, sometimes when the initial object has structure, we can shift that structure to the quotient by simply translating the structure. So in this case, k of x has a ring structure. We can add and we can multiply polynomials. So there's a way of defining addition and multiplication in the quotient set, just like we did in finite fields. K of x over the relation can be endowed with addition and multiplication in the only way possible that we can imagine. Okay, so how do we add the class of H and the class of G? Well, it can be seen that taking the addition of the polynomials and then taking class, right? And multiplication can be defined similarly, right? How to multiply two classes? Well, what you do is take H, multiply by J, by G, and then take the class. This makes the quotient a ring, a commutative ring, first of all, and then it makes the projection a ring homomorphism. A little bit of notation, we'll just refer to this quotient and we'll write it as k of x over f, which is the one that we are fixing, okay? So we have this new ring. This guy is a new commutative ring that we have built out of f and out of the polynomial ring k of x. So now what we need to say is, okay, we're going to show that this contains a copy of k, and we're going to show that this has a root for f, okay? And now it's time to look at how the projection works. Take an element in K, look at it as a constant polynomial, and then you project it to the quotient ring. So what we are seeing now is that there's this sort of way of looking at constants as constant polynomials and then pulling that polynomial down to the quotient. In that sense, the collection of classes of constants with B being K is a copy of K inside the quotient ring. We're just looking at constants as the classes of the constant polynomials. So in that sense, K can be seen as included in this quotient ring, okay? Observation: this inclusion is an injection. So different constants go to different classes. Okay, so that's the first thing. But then this quotient ring contains K, but we need to prove that it's actually a field. We need to prove that this quotient ring is really a field. And now we are going to use the irreducibility of f. Now we invoke the irreducibility of f. And this is very simple. Let I don't know. Let g belong to k of x such that the degree of g is strictly less than the degree of f. Okay? Now we're going to use the Cauchy-Bessoud theorem. And we're gonna say this in this order. Okay? F irreducible says that G and F have no common factors. Other than 1. Okay, F is obviously divisible by the constant 1, also G, but since F is irreducible, it has no non-trivial factors. In particular, whatever factor G has, and we're sure it's not a factor of F. So G and F have no common factors other than 1. And now the Cauchy-Bessoud theorem for polynomials says that there exists A and B, polynomials in k of x, such that A times G plus B times F equal to the polynomial 1. And this is an identity in k of x. And since this is an equality in k of x, we can project it to the quotient. So we will project the left-hand side, and it has to be the projection of the right-hand side. And now we use the properties of the projection. The projection of the sum is the sum of the projections. And now the projection of the products is the products of the projections. And now we take a look at this part, right? The class of f is actually the class of 0. So what we get is that this guy over here is simply the class of 0 and then vanishes. And as a result, the class of A times the class of G equals the class of 1. And what is saying this? It says that every non-zero class has a multiplicative inverse. The class of A is the multiplicative inverse for the class of G. So what we have seen now is that whenever f is irreducible, if we take any polynomial of degree less than f, then it will have no common factors with f. So Cauchy-Bessoud allows us to write it this way, and then the projection does the rest. So every non-zero class in the ring k of x over f has a multiplicative inverse. So we have shown is that k of x over f is not only a commutative ring, but it's also a field. This is a field. What's left, the only thing left to be shown is that it contains a root for f. And this is not complicated because you can take x that belongs to k of x. This is the polynomial consisting just of x, and then you project it to the quotient field, and what you get is the class of x. With the convention that the class of the constant should be called the same as the constant for every b in k, then what happens when you take a look at the polynomial f of x, written as this? And now we can watch this polynomial as belonging as a polynomial in this field, polynomial, since all these coefficients can be seen as belonging to this field, so we have this field x, then what happens when you evaluate the polynomial in the element x bar. So this is simply by substitution this, and which in turn is actually a over I, and then you have x to the I power class, because class commutes with products. And now you remember that the constants are the classes of the constants. And now you remember that classes are compatible with products again, and classes are compatible with sums. And this is simply the class of f of x. And in this field, this is the zero class. That is the zero class. So for the polynomial f, the class of x actually works as a root. In this field, the class of x is a root of f. So this field contains a copy of k and also contains a root of f. So we were able to construct a new field out of a given field, and an irreducible polynomial that contains a copy of the original one and also contains a root of f. So by repeating the same process, we can find a field that contains every possible root of f. So this finishes the proof. Observation: by repeating this process, we can obtain a field that contains all roots of f, and that is called the splitting field for f. And that is a process that finishes in finitely many cases because f has finitely many roots. So that's a finite extension, of the base field K containing all roots of f. And it has just that, okay? In the sense that it is minimal among all the fields that contain the roots of f. So this process of actually constructing fields that contain roots of polynomials is a very important one. Okay, examples of this, we have many. Examples, take for instance x squared minus 2, which can be seen as belonging to q of x. If we take the quotient of q of x over f, we get a field that contains the roots of this polynomial, and that field contains q and also contains square root of 2. It's a finite extension of the base field. Then we can also take a look at f of x squared plus 1 for simplicity. F is a polynomial with real coefficients, and when we take the quotient of r of x over f, what we get is the complex numbers. It has r and then things that can be written with I. Okay, so in this case, the class of x, we call it square root of 2, and in this case, the class of x, we call it I. So the class of x will always work as a root for the polynomial. Okay, this can also be done with finite fields. Okay, this can also be done with finite fields, and then we build fields that have more than a prime number of elements. Say, let's find f of x, x squared plus x plus 1. Okay, so this polynomial is irreducible in set 2 of x. It has no roots. If you evaluate it at 0, or the class of 0, you get 1, and if you evaluate this in the class of 1, you get also the class of 1. So f has no roots. Having roots and being irreducible is only equivalent for polynomials of degree 2 and 3. Okay, so be aware. And now you just take the quotient and this ends up being a finite field that contains contains set 2 and a root for f. And this can be seen as all the combinations with set 2 coefficients of the class of 1 and the class of x. All the polynomials, well, not all, but polynomials with degree less than 2. So here we can have the class of 1, the class of 1 plus x, the class of x, and we also have, which one? We're lacking 1. And 1, the 0 element, okay? So this field has 4 elements. And 4 can be thought as 2 to the power of 2, which is number of elements of the base field to the degree of the irreducible polynomial that we use to construct this new field. In general, for set p of x over f, then you have just p to the degree of f elements. So we are now in position that we can construct fields of order p to any natural number that we have a polynomial, an irreducible polynomial of that degree. Okay? So I think this is okay for today. We are gonna have more videos of this, and maybe we can cook some examples showing more fine fields doing this. But we are now headed to factoring polynomials and opening the door to a new thing that we're going to do is see how we can use polynomials to interpolate data. Polynomials are a very powerful tool to interpolate, and that can be used to codify information, to hide information in large sets of numbers. Okay, so that's going to be really, really interesting. Hopefully in a couple of videos we're going to be taking a look at that. Okay, so I hope you enjoyed this, and see you in the next video. Goodbye.